All right, so I heard you guys got a Rubik's Cube for Christmas, and as you might notice, there are 6 surfaces, as there are 6 colors. Some other fun facts are there are 12 edges and 8 corners. So with all of these components of the cube, did you know there are 43 quintillion ways to solve a cube? Um, and I'll break it down how you get to that number. So let's first disassemble the cube, and this is how it looks when it's not pieced together and you've got a core. The core doesn't really matter to the solving, like the permutations, because they're already locked in place, but they do offer as a reference point. So as you can see, the rule is that the colors must be arranged appropriately according to their relationship. So red and orange are always opposite of each other. White and yellow are always opposite of each other. Green is always opposite of blue. There you go. And to start filling in this core, you can start with the edges, and an edge piece has 2 colors. And with corners, there are 3 colors. There you go. So I'll go ahead and write what I'm talking about here. We have 1 core, oops, which is kind of irrelevant to the formula here, and 12 edges and 8 corners. There you go. And each time that we insert one of these pieces, the arrangement's possibilities are less. So this is what I'm talking about. If I have 1 edge in, and I go to put in another edge, now I only have 7 possibilities, or 7 arrangements. Now that I've got 2 edges in, I have 6 possibilities. So you just go down the order of things, and instead of writing 12 times 11 times 10 times 1, you can just say 12 to the, not 12 to the, sorry, 12 exclamation mark. It's a quicker way of writing, oh man, that whole strand out. So this is called a factorial. With corners, it's the same way. And then something else to bear in mind is that the arrangements are more than just their placements. Those placements are their permutations. Orientations actually looking at how many ways they can be swapped, or not swapped, sorry, excuse me, switched or flipped. So with an edge piece, it can be arranged like this, white and blue, or blue and white. And with the corner, there are 3 colors, so there are 3 possible ways of rotating, flipping this. And so to write that out mathematically, you would have, for the edges, 2 arrangements for 12 of those total edges that we counted in the beginning. And then for the corners, there are 3 arrangements, 3 colors, with 8 of those elements that we counted in the beginning. So you multiply all of that out, and it's going to be over 43 quintillion. But this is only counting for just assembling the cube. It's not solving the cube. When you get to the last part, once you assemble everything, the very last piece of the edges and corners must be inserted in its correct permutation. So there's less flexibility on the last one. So you might actually write that as 2 to the 11th possible arrangements, or 3 to the 7th possible arrangements. And the pieces are still there. So it's 8 factorial and 12 factorial. There you go, you multiply all those. And another thing is, I think this will get you the, it's still not quite at the solvable state yet, but it's going to get you to the completed assembled cube. But to account for the end, like the issue with these swapped and flipped corners and edges, because with a 4x4 you can have that, but with a 3x3 that's not possible. And so we're going to divide these by 2. Now, if you plug and chug all of this into the calculator, you will get 43 quintillion, 252 quadrillion, 3 trillion, and 274 billion, 489 million, and 856,000. So that's a lot of possibilities. Can you imagine how big this number will be? Ta-da! There you go.